स्क्रीन शेयर होते स्टूडेंट्स. So good morning students. We are studying ion carbon equivalent diagram. In this basic ion carbon equivalent diagram, we are going to understand what is exactly ion carbon equivalent diagram. Just a minute. Students screen share झाला का रे? Students, hello. Students screen share होते काय?
Yes,
हो,
sir.
येस सर.
Students
स्क्रीन
ion
शेअर नाही
carbon
झाली
diagram
सर.
repeat नाही झाली का? Just मी screen share करतो बोलतो. Just wait.
झाली सर स्क्रीन शेअर.
झाली ना? तेव्हा दिसतं स्क्रीन शेअर. आयन कार्बन डायग्राम दाखवली बघा. हा महत्वाचा पार्ट आहे एमईएमचा, त्यामुळे मी रिपीट करतो परत एकदा. So we are studying this ion carbon equilibrium diagram, also called as Fe3C diagram. So at here on this x-axis there is a weight percentage of carbon. Carbonचं percentage मध्ये बरोबर आहे. There is a composition of carbon in weight percentage, like from 0% that is plain carbon steel up to 6.67% of carbon in that steel. So that is weight percentage of carbon. And on this axis, on this y-axis, there is a temperature in degree Celsius. Temperature आहे degree Celsius as well as in Fahrenheit also. In both units, there is temperature. And this ion carbon diagram shows these three critical temperatures: lower critical temperature, medium critical temperature, and upper critical temperature. As at these three critical temperatures, these are the three reactions. So that we have to study one by one today. So there is a peridactic point at the higher temperature, around this 1495 degrees Celsius. Around this 1495 degrees Celsius, that solid steel is converted into completely liquid steel, that is liquid phase. So there is a peridactic point is there. Then orthorhombic ion atoms are blue. Orthorhombic structure असतं. That cemented structure is orthorhombic structure that is showing it on the diagram. The structure of pure ion at room temperature is called as alpha ion. Alpha ion कुठे असतं? That alpha ion is at this pure form of room temperature. At that room temperature, at this normal temperature, that is pure form, that is 0% of carbon, that is alpha phase or called as alpha ion. So this alpha ion is a pure form of ion. Ferrite is soft and ductile. Normally ferrite is very soft and ductile. Since ferrite has the alpha ion has BCC structure, body centered cubic crystal structure. The ion atom spaces are small and pronouncedly oblate and cannot readily accommodate even a small carbon atom. Therefore, solubility of carbon in ferrite is very low. It is of the order of 0.006 at 0.06% at room temperature. Its solubility is very slow because of the BCC structure, that is body center cubic crystal structure. Now the maximum carbon content in ferrite is 0.05% at the 727 or 723 degrees Celsius. You can see in this ion carbon diagram at this constant temperature line called as 720 degrees Celsius. And maximum carbon percentage is up to 0.0. So it is up to 0.05% of carbon at this alpha ferrite phase. Now, in addition to carbon, certain amount of silicon, manganese, and phosphorus may be added in ferrite. May be found. For alloying element like silicon, manganese, phosphorus also there in carbon and as an alloying element. The phase-centered modification of iron is called as austenite or gamma ion. Is above this 723 degrees Celsius. You can see students at around this 910 degrees Celsius. Beyond this 910 degrees Celsius, the alpha ferrite phase. This alpha ferrite phase is converted into gamma austenite. This alpha ferrite phase is completely converted into the gamma austenite beyond this epiphtide point and above this 910 degrees Celsius. So this gamma austenite is a gamma phase. It is again in the FCC structure. This gamma austenite with gamma ion, it is a stable form of pure iron at temperature between 910 and 1400 degrees Celsius. And its stable temperature austenite is soft and ductile. Stable temperature austenite is soft and ductile and consequently is well suited for manufacturing processes. The phase centrifugal structure of iron has longer or larger inter-atomic spacing than in ferrite. Even so, in FCC structure, the interstitics are barely large enough to accommodate carbon atoms, and lattice strains are produced as a result of not all the interstitial sites can be filled at any one time. That is FCC structure of iron, that is gamma austenite. The maximum solubility is only 2% of carbon at 30 degrees Celsius, 103 degrees Celsius. It is gamma austenite phase. And above this 1400 degrees Celsius, this austenite is no longer and more stable form of iron, and the crystal structure changes back to the body center cubic structure, also called as delta iron. Again, that FCC is converted into the BCC structure called as delta iron. This is the same phase of alpha iron except for its temperature range. This delta iron and alpha iron, they are both same, only is the temperature changes. The alpha iron is at room temperature or up to 727 degrees Celsius, but at this 1400 degrees Celsius, that phase is called as delta iron, which is again BCC structure. That is body centered cubic crystal structure. Now the solubility of our carbon in delta iron is small, delta ferrite is small, but it is appreciably larger than alpha ferrite because of higher temperature. The maximum solubility of carbon in delta iron is 0.1%, that is at 1490 degrees Celsius. Now in carbon alloys, carbon in excess of the solubility limit must be second phase, which is called as iron carbide or cementite. The iron carbide or cementite is the Fe3C base. This does not mean iron carbide forms molecules of Fe3C, but simply that the crystal lattice contains iron and carbon atoms at 3 to 1 ratio. 3 ferrous atom and only one carbon atom. That is 3 to 1 ratio. The compound Fe3C has an orthorhombic unit. Cementite structure कसं असतं? There is orthorhombic unit cell with 12 iron atoms and 4 carbon atoms per cell, which has a 6.67% of carbon. As compared to austenite ferrite, cementite being an intermetallic component, it is very hard and brittle. The presence of iron carbide with ferrite in steel generally greatly increases with the strength of steel. In the reaction, the simultaneous formation of ferrite and cementite form austenite results at the temperature of 727 degrees Celsius and composition of 0.80% of carbon. There are nearly 12% of iron carbide and slightly more than 88% of carbide in the. Since the ferrite and cementite are mixed simultaneously, they are intimately mixed. Characteristically, the mixture is lamellar and it is composed of alternate layers of ferrite and cementite. The microstructure is called as perlite, which is very important in iron and steel technology because it can form almost all steel by means of suitable heat treatment. Now, the alloy containing 0.80% carbon is also called as utilitarian steel. Upon cooling the utilitarian steel below 70 degrees Celsius, all of the oxygen is transformed into perlite. Alloys with less than 0.83% are called as hypoeutectide, and with this higher composition are called as hypereutectide steels. Fe3C diagram is characterized by five individual phases. Alpha ferrite phase, that is BCC structure, FEC solid solution, then gamma austenite phase, FCC solid solution, then delta ferrite phase, again FEC solid solution, and Fe3C iron carbide or cemented and intermediately compound and liquid FEC for invariant reactions. These are the three reactions. Peridactic reaction at that high temperature, that is 1495 degrees Celsius, and 0.16% carbon. The delta ferrite plus liquid goes rise to gamma ion austenite phase. That is the peridactic reaction or called as high temperature reaction. Then monotactic reaction, that is again at that this high temperature, the liquid is goes rise to liquid plus gamma ion. That is monotactic reaction. Then eutectic reaction at that medium temperature line at this 1147 degrees Celsius and 4.3% of carbon. The liquid is gives rise to gamma ion plus Fe3C cementite phase. Cementite plus lidopyrite. That is a medium temperature reaction. And this eutectide reaction at that low temperature reaction or at this 723 degrees Celsius and 0.8% of carbon. This gamma ion changes like to alpha ferrite plus cementite called as a perlite phase. So three phase reactions. These are the topics. It denotes at least one liquid phase is there. And avoid all phases involved are solid. So, so these are the important ion carbon equivalent diagram. So students, this ion carbon equivalent diagram is important part for any studies. Just a minute, we'll again see some. So you can see students, this is ion carbon equivalent diagram in detailed structure. At here there is a Fahrenheit temperature in Fahrenheit as well as temperature in degree Celsius also. So this is your ion carbon equivalent diagram. You can see students at here there is a weight percentage of carbon, and carbon percentage from 0% from plain carbon steel to 6.67% of carbon. So up to 2% of carbon, the metal is called as a steel, and above 2% of carbon, there is a cementite phase, which is very hard and bitter. That is your cast iron. So that cast iron from 2% onwards up to 6.67% of carbon. That is cast iron, students. Student, these are the different phases. These are the different phases which involved in the ion carbon equivalent diagram. First is liquid solution of carbon in iron. That is liquid phase, or called as delta ferrite phase. Delta ferrite phase. Hmm? कमी आला? Delta ferrite phase or solid solution of carbon in iron. The maximum concentration of carbon in delta ferrite is 0.09% at 2790 degree Fahrenheit or 1493 degrees Celsius. The temperature of the peridactic transformation. Peridactic transformation at higher temperature reaction. The crystal structure of delta ferrite is BCC structure. Then austenite or called as gamma austenite. This interstitial solid solution of carbon in gamma ion. The austenite has FCC structure or cubic phase crystal structure, phase centered cubic crystal structure, permitting high solubility of carbon up to 2.06% at this 1147 degrees Celsius. And austenite does not below 1333 degree Fahrenheit or 723 degrees Celsius. It is maximum carbon concentration at this temperature is 0.83%. Then alpha ferrite phase solid solution of carbon in alpha ion. The alpha ferrite is BCC structure and low solubility of carbon up to 0.025 at this 723 degrees Celsius. And alpha ferrite phase does not exist at temperature. room temperature. There is a cementite phase, alpha iron carbide or intermetallic compound having fixed composition of Fe3C. Cementite is hard and brittle substance influencing on the properties of steel and cast iron. The following phase transformation occur in the carbon alloys. So student, these are the three critical temperatures. Upper critical temperature, upper critical temperature that is ACM, the lower critical temperature and magnetic transformation temperature that is ferromagnetic. So these are the three critical temperatures. A3 is the below is the ferrite starts from 2 as a result of injection of austenite in the hyperprotected steel that is upper critical temperature. The upper critical temperature ACM, the temperature below which the cementite starts to form as a result of injection of austenite in the hyperprotected steel, and there is a lower critical temperature. Temperature of the austenite to perlite filtration below the temperature. Austenite doesn't like this. Then magnetic transportation temperature. It is the temperature at which alpha ferrite is ferromagnetic. So these are the number of critical temperatures. Then phases com- composition of iron carbon alloys at room temperature. It is hypoprotected steel and hyperprotected steel. Carbon containing 0.83% of carbon. That is perlite phase. And cast iron is having 2.4 percentage to 4.3 percentage. Consists of ferrotite, cementite ejected from the ACM curve. So in this way, student, this ion carbon equilibrium diagram is important part for your further studies. बरोबर? हे थोडक्यात आपण परत एकदा बघू स्टुडंट आयन कार्बन इक्विलिब्रियम डायग्राम. On this x-axis there is a weight percentage of carbon. Carbon is in the weight percentage, right from 0% up to 1, 2, 3, 4, 5, 6, and in between 6 to 7 that is 6.67%. Importantly, that is up to 6.67% of carbon. That shows the allotropic nature. That in this ion carbon diagram, on x-axis there is weight percent of carbon, on the y-axis there is a temperature in either degree Celsius or either in degree Fahrenheit. So, with respect to change in weight carbon percentage and change in temperature, the ion shows the different phases. Ion shows the different crystal structures. So, this property of ion is called as entropy of ion. The entropy of ion is showing different crystal structures, showing different phases at different crystal structures. That is the entropy of ion, and you can see that from the zero temperature, from sorry 0 degree Celsius, there is a perlite phase or ferrite phase. There is alpha ferrite phase, and above this 726 degrees Celsius, this constant temperature line having less carbon solubility from only 0.025% carbon solubility, showing the alpha ferrite phase, and above this 726 degrees Celsius, this alpha ferrite phase is converted into the gamma austenite phase. Above this 910 degrees Celsius, at this 910 degrees Celsius, this alpha ferrite phase is completely converted into the gamma austenite phase. This gamma austenite phase will be there up to 1400 degrees Celsius. Up to this 1400 degrees Celsius, this gamma austenite phase is converted into the delta ion, or called as liquid phase. The liquid phase above this 1493 degrees Celsius, that solid steel is converted into the liquid steel, that is delta ion. So this alpha ferrite phase is having BCC structure, body center cubic structure, and this gamma austenite is again having this S cubic structure, and again this delta ferrite is having this body center cubic structure. So this part of this property of iron showing different crystal structures at different temperatures as well as at different crystal carbon content is called as a soltropy of iron. Sorry, altropy of iron. This altropy of iron is having different crystal temperatures. So just a minute, students. This is again iron phase diagram, iron carbon phase diagram, having different crystal structures at different So these are the different crystal structures. When we see under microscope खाली जेव्हा बघतो आपण, so we can see these different crystal structures at this different temperature. Now, this alpha ferrite phase and this delta ion is very similar. Only the temperature difference is there. At here there is a normal temperature from to 727 degrees Celsius, and at this higher temperature, that solid steel is converted into liquid steel at this 1490 degrees Celsius. So that is a liquid phase is there. That is delta ion. But the crystal structure is BCC again. That is body centered cubic crystal structure. Whereas this gamma solid phase is having gamma phase or having FCC phase centered cubic crystal structure. And this point is called as a eutectide point, hypereutectide and hypoeutectide point, hypoeutectide and hypereutectide point. Similarly, this point is called as eutectic steel, eutectic point, hypoeutectic and hypereutectic point. These are the important parts of your iron garment diagram. So this is
When a molten metal solidifies, the atoms arrange themselves into definite patterns called crystal structures. The two most common crystal structures in metals are body-centered cubic and face-centered cubic. These crystal structures grow uniformly in all directions within each developing crystal. As the metal cools, these crystals are confined by the adjacent developing crystals, forming grains. The line of intersection between grains is called a grain boundary. Because the grains form independently, their crystal structures develop tilted in various directions. All atoms in these crystalline structures are held in place by electromagnetic attraction to neighboring atoms. If a force or load is applied to a metal, these electromagnetic bonds stretch, allowing the atoms to move slightly. When the load is removed, the bonds pull the atoms back into position. If the applied force exceeds the metal's yield strength, those electromagnetic bonds will break, causing permanent stretching or deformation. This diagram is the iron-carbon phase diagram. Let's examine how temperature and carbon content combine to provide a variety of metallurgical structures. The left-hand side of this diagram is ferrite. Ferrite is iron containing an extremely minute amount of carbon. At room temperature, ferrite is magnetic, relatively soft, and has a body-centered cubic crystal structure. At room temperature, the solid solubility, or the amount of carbon that can be dissolved in ferrite, is practically zero. The amount of carbon dissolvable in ferrite increases to only a maximum of 0.025% at 1,333 degrees Fahrenheit. When heated to 1,670 degrees Fahrenheit, ferrite's body-centered cubic crystal structure rearranges itself into a face-centered cubic structure, known as austenite. This transformation to austenite is an important phase in the heat treatment of steels. Austenite's crystal structure allows it to absorb up to 0.80% of carbon at 1,333 degrees Fahrenheit, increasing to a maximum of 2.0% at 2,066 degrees Fahrenheit. The right-hand side of this iron-carbon phase diagram represents cementite, also known as iron carbide. Cementite contains 6.67% carbon. Though this phase diagram ranges from ferrite, with very low carbon content, to cementite, with 6.67% carbon, most steels contain less than 2.0% carbon. The carbon content is the major factor in determining the properties that can be developed in steel. The use of very low carbon contents or very high carbon contents provides many different steel compositions with very different properties. For this reason, steel is suited to a wide range of engineering applications. Let's take a closer look at some examples of how carbon affects the hardness of steels. If steel containing 0.030% carbon is heated to about 1,700 degrees Fahrenheit, the structure will consist entirely of austenite. If it is then cooled slowly at about 1,650 degrees Fahrenheit, the austenite begins to transform to ferrite. As cooling continues, more and more ferrite is formed, until at 1,333 degrees Fahrenheit, the remaining austenite transforms completely. Ferrite can retain only 0.025% carbon at this temperature. So to accommodate the carbon in excess of this amount, the remaining austenite transforms to a mixture of ferrite and cementite in alternating thin, plate-like layers. This structure is referred to as pearlite. At room temperature, the steel is mostly ferrite with patches of pearlite.
So in this way, students, important part of ion carbon equivalent diagram. So just a minute.